Hello and welcome to Oracle Database World. I am Anil Nair. Today we'll be talking about future-proof your applications using Oracle Rail Application Clusters. I am the product manager for RAC and Automatic Storage Management. I've discussed these requirements of future-proof applications with developers, DBAs, and IT managers, and this is some high-level steps that I think are requirements for future-proof applications. The first requirement is the ability to scale both vertically and horizontally while being available. Scaling vertically basically involves the ability of an application to scale as more and more resources are added to it. For example, add more CPUs or add more memory. And this is a very critical requirement for future-proof application because applications can become very popular and can have more and more load. So we want to make sure the SLAs are kept. So therefore, we want to make sure that applications that are future-proof have the ability to scale vertically. Now, remember that there are limits to adding resources to a single server. So there needs to be this additional capacity or capability that these applications should be able to scale when we add more and more nodes in the cluster. So this is called the ability to scale horizontally. Of course, all of these things have to be done while the application is running. That means there should be no need to stop everything, add resources, and restart again, which in other words means it should be highly available. The second requirement for future-proof application is the ability to support a variety of programming languages and APIs. Now, as you know, over time, certain programming languages get more popular with developers than others, and they keep changing the most popular language. So it is important that the future-proof application support a variety of programming languages. The third is the ability to optimize the different kinds of workloads. Now, if you take the most common type, which is OLTP, online transaction processing, or analytics kind of workload, they have a little bit different requirements in terms of the resources and how they use the resources for scalability. Now, the application would be future-proof if we had a way by which we could define certain workloads as OLTP and analytics and even hybrid workloads. So these can be actually scaled and highly available. Finally, this is one of the most important criteria, which is the support for deployment on a variety of platforms. Certain customers have made their default implementation choice as Linux or Windows or any other operating system. And then obviously there is this requirement that should be even in the cloud. And so one of the future-proof capability for applications should be that it should be available on a wide variety of deployment platforms. So let's answer, what's the easiest way to future-proof your application? Well, I would say standardize it on Oracle RAC. And why do I say this? Well, I say this because let's say you have a two-node RAC cluster. Okay, this is the most common type of deployment, and you start deploying applications. When you deploy an application, we expose it as a service. A service is an endpoint to which an application connects to the database to do their insert, update, delete transactions. Now, if you remember the word services, developers are more familiar with the word microservices. So this is kind of similar in the database world. So you are essentially putting some of your applications and exposing them as services for the application to connect. Now, as you deploy more and more of your applications in the RAC cluster, you see that we have added more services. Eventually, you get to a point where you have pretty much used up all the resources of a two-node RAC cluster. Now, in the past, without a RAC cluster, what would happen is somebody would need to replace the entire server because there is no way to add more resources to it. Well, luckily with RAC, what we can do is we can actually add a third node dynamically without any downtime and continue our deployment so that you can move more and more of your applications, expose them as services to the different nodes of RAC. Now, remember, the reason why I said the easiest way to future-proof your application with Oracle RAC is because it provides you the two critical requirements. One is the scalability aspect, which is both vertical and horizontal, and the high availability aspect, which is both for planned downtime and unplanned downtime. Planned downtime operations are something like you take an outage because you want to say apply a operating system patch to your server or replace, let's say, a network card. Unplanned is when the network card itself goes offline because of some problem, and therefore needs to be the node goes down, or maybe some other critical component of the server goes down. So regardless of how the issue occurs, we are able to provide, as in Oracle RAC is able to provide both the scalability and high availability. So just to summarize again, how does Oracle RAC help future-proof applications? Well, the database, Oracle database single instance, supports a lot of different types of application deployments. Like, for example, you could have a JSON-based application, or a blockchain-based application, or even a queue-based application, or an IoT-based application. Regardless of what application you have, we are able to deploy them on different nodes of RAC. We provide the capability to add instances as needed. We also provide the capability for zero downtime during maintenance operation. And obviously, Oracle RAC supports all the programming languages that Oracle Database supports. So we do have inbuilt support for a variety of programming languages. We have a variety of deployment choices. You could deploy it on Solaris, AIX, or in the Oracle Cloud, which is what our preferred recommendation would be. And all of this without changing your application. There is no need to change anything in your application to get it working on Oracle RAC. So obviously, the first question would be, hey, Anil, this is all good, but how does Oracle RAC scale all workloads? How is it able to do what others cannot? Well, what we have been doing in Oracle RAC development team has been that we've been constantly improving the algorithms and seamlessly adapting them to modern architectures. So let's take this example of this, CPUs. Now, CPUs over the last 20 years, has seen a tremendous change. You have a lot more cores in the CPU, and then these cores have multiple threads. So the operating system provides the capability for each of these threads to a parallel set of execution that can go on without interrupting each other. So what we have done is we went back to our processes and made them more fine grained. What does that mean? So the LMS has some functionality or fulfills some functionality in Oracle Real Application Clusters. So by making them split that functionality into more processes and the ability of those processes to dynamically spawn threads based on incoming workload, makes the whole workload scalable, because we are now able to run concurrently. The second one is the distribution of workloads across instances. So we have talked about this earlier, that Oracle RAC, you can have certain services running on certain nodes. Now think about it this way. If you have an OLTP service, you could run it on, say, node 1, and an analytics service you could run on node 2. So users who want to run analytical queries can connect to node 2. Because the reason this is a really good advantage is because an OLTP workload has a different requirement than analytics. For example, the SLAs for OLTP dictate that the insert, update, delete, complete as fast as possible. And analytic workload would typically run jobs that go on for a long time in order to get you whatever analytical report that you're running. An analytical, typical analytical queries, we would use more swap space or more temporary table space, or require more memory for their swapping operations. So there are different requirements, and the good thing is Oracle RAC allows you to distribute them across different nodes. In fact, you could have node 1 more, more optimized for OLTP, while the analytics analytics instance could be more optimized with more number of cores and more number of more random access memory, so that you could actually contain all your sorting requirements in the server. So this is an amazing way by which you can make sure that your OLTP application or workload is running as fast as it can, while the analytics workload is running as optimized and fast as it can. The third way by which we scale workloads is by constantly and dynamically doing or optimizing our internal workings. What I mean by that is, As you know, Cache Fusion provides the ability so that a query that connects to a certain node can get the block from the remote node and provide the response to the query, all without the query itself knowing about what's going on internally. Now, imagine that if at certain point of time, as shown in the image, that a user is running a query, and the query requires a block that is cached on node 2. So in this case, let's say at that point of time, there is some kind of congestion on the private network. So Cache Fusion knows about this and therefore may let the query be fulfilled by reading directly from the disk. Now, in this case, I've taken the liberty to mark this specific architecture as using some kind of SSDs. Now, you know that SSDs are extremely fast than the rotating disks that we are used to in the past. So essentially at this time, our Cache Fusion would determine that, hey, my latency on the IO is much faster than the congested private network. So let me satisfy this query by reading from disk directly. And this, by the way, is dynamic and does not require any kind of user intervention. And by the way, once the congestion is gone and we notice that the private network is much more faster and there's no congestion, then we would go back to using it. And finally, I want to talk about a bit about our Oracle RAC deployment on Exadata or engineered system. Now, this is really one of the best platforms for RAC because we are able to use what we call as RDMA. Now, what is RDMA? So let's simplify it. DMA is direct memory access, and processes in a server are able to access the memory using DMA. RDMA is the way by which we can do or access the memory from the remote node. So it's like R as in remote direct memory access. Now on Exadata system, we even make it better by using this thing called Exafusion. Now Exafusion provides the ability for Cache Fusion to use RDMA to directly access the remote memory, bypassing the operating systems. So there is no context switch, and therefore we get extreme performance. So this is really something that we are using all the capabilities of the latest and greatest in hardware and the improvement in our algorithms that makes it possible to scale all different types of workload. Over the years, RAC has been out for about 20 plus years, and over the years, we have actually come up with a lot of features, and this is a very small subset of the features that we have introduced over the years. Now, we are not going to get into details about every single feature here, but we'll talk a bit about some of the features that result into amazing performance benefits, and that's where we get into Oracle Real Application Clusters performance optimization. Now, as you can see, I've again taken a small subset of performance optimizations here, and I've taken, spread it across different versions. Now, I've seen that some were introduced in 12C, some in 18C, and 19C and 21C. Obviously, some are specific to Exadata because it requires the use of RDMA. I'll mark them down so that you know which are Exadata specific. As you can see, there's a good balance between the Exadata specific features and the features for your generic systems. Now, think about it this way. Let's take the most common case that affects scalability of OLTP systems. This is mostly because of the overhead of index maintenance. So what does that mean? So when you have an OLTP system, you're inserting records as your orders come in. And if you have an order number which is increasing monotonically, then as the new orders come in, this order number increases, let's say from 1, 2, 3, 4, all the way to 100, 101, and all that. The problem with this, it comes in when you have an index on order number. Now, if that happens, then we need to constantly maintain the B-tree index. Now, the B-tree indexes needs to be balanced. What that means is balance is the way by which we can access the actual record when we are selecting using that index to be able to get that answer as quickly as possible. The problem in the past without this feature was that the B-tree indexes would get unbalanced and therefore performance may suffer. The index contention optimization basically improve on this. So we have added a lot of changes to our algorithms. We added new algorithms, improved the old ones so that the during your insert, update, delete operations, even when they are executed from different nodes, we try to reduce this contention. And there is a we have written a bit of details of this in this white paper that you can see below, which is a bit specific to Exadata, because some of these features does use the Exadata features, but then overall the index contention optimization will help even on generic systems. The other one that I want to talk about is in 21C. That is in 21C, we are even doing what we call as broadcast and commit using RDMA. So broadcast and commit is the capability by which if you are inserting, updating, deleting on different nodes, then every time you do a commit, the SCN needs to be updated across all the nodes. And this used to be sent as a message in the past. But in 21C with Exadata, we are going to use RDMA for that, which would reduce the number of instructions that is required and therefore make it easier to scale. I talked a bit about the way that we monitor the resources, and the actual process that does the monitoring uses this framework, which we call it as Oracle RAC Database Reliability Framework. What is this reliability framework? Well, the database reliability framework has four main functions, which is to monitor the resource usage, adjust them, adapt to changes, and tune them. So at a very high level, we monitor the usage of the resources like CPU, memory, internal memory structures, and then we optimize it to make sure we optimize the CPU usage. So, for example, if there is a lot more CPU, and if there is a lot of LMS congestion messages, then we want to make sure that we can spawn more LMSs. This helps us to reduce brownouts, because remember, if we didn't do that, eventually the system may get overwhelmed and cause crashes. While we are dynamically adjusting the internal parameters in internal memory structures so that future memory allocations are much more optimized. So let's look at this with an example. As I said, let's say that the monitoring capability of a database reliability framework found out that there is a GCCR block congested wait event. This wait event generally means that the LMSs are not having enough CPU to or need more CPU to be doing their job faster. So obviously what we can do, what DRF does is it tries to find out things that it can do to reduce the CPU usage. For example, it could reduce or disable DRM. DRM is this capability of dynamic resource mastering, which does require everybody to quiesce their CPU usage, but at that time, it may increase the SLAs and the latencies of these transactions, and therefore the right determination taken by the database reliability framework is to disable DRM temporarily until the CPU usage comes back to normal. And as you can see in its cycles, it is trying to check whether we should do the enable DRM by checking the CPU load. So this is something that again happens automatically without any user intervention. Continuing on this path, we also try to provide you this feature of what we call as PDB isolation for scalability. Now, as you know, that more and more customers are trying to use PDBs, deploy PDBs as microservices, and put a lot more PDBs in a database. Now, when this happens, you are obviously going to put all your eggs in one basket. So definitely it makes sense to use RAC, because now you're protected. You're not just protected from the PDB aspect of it, but we also provide you features in terms of PDB isolation and scalability. Now let's understand this through this image. First of all, when you have multiple PDBs, we provide you as a DBA to provide us with placement policy, start order, and rank. So essentially you can say, hey, my gray PDB is the most important PDB, so I want it to be started first after instance or when server starts. And I want it in a certain order. So we have a 3-node cluster here, and we have 3 PDBs. We have a yellow PDB or PDB1 running on instance 1, and we have the red PDB running on all the instances, and the gray PDB running on instance 2 and 3. Now, obviously, the PDB1, when it's running on instance 1, and let's say instance 2 crashes for any reason, the PDB1 does not even have to go through what we call as a reconfiguration, because all the changes for PDB1 is already on instance 1. So essentially, we are making sure that when you consolidate, you do not affect the reconfiguration time. Also, because the gray PDB is running only on instance 2 and 3, the DLM messages are only sent to instance 2 and 3 for the gray PDB, because we know that there is no PDB running on gray PDB running on instance 1. So this, in a sense, gives us a complete isolation in consolidated environments. We also have this feature, called Oracle RAC Cache Fusion Hardening, which essentially tries to prevent costly instance crash. Now, what is costly instance crash mean? Lately, we have seen customers are using a lot of big servers. When I say big, I intend to mean I mean to say the servers with a lot of CPU and memory. So when you have this huge 1 terabyte SGAs and with hundreds and hundreds of CPUs, the server takes a while to start up. And so what we need to do is prevent it going down in the first place. So we have been constantly improving our cache fusion algorithms to catch some of the common cases. Now, one of the case that we catch is the case where cache fusion finds out the block that it requested is not exactly what it wanted. Let's take an example and go through this animation. So we have a 2-node rack cluster, and we have a cache fusion going on between these two systems. Now, let's say we have this block B in green, and instance 2 says, hey, I want that block. Now, as the block is sent over, you can see that the block becomes red, which is essentially that, hey, I wanted the green block. How come it became red? Now, this is something that is detected by instance 2. And in the past, without this feature, we would eventually go through what we call as a Aura 481 and crash the instance, because we don't know why this green one turned into, or was changed. But with this feature, what would happen is this cache fusion process would resend the request saying, hey, wait a minute, let me send it to you again, with the idea that resending the block may may fix the anomalies, and therefore prevent what we call as instance crash. This is something very interesting and cool feature, which tries to reduce the chances of an instance crashing due to an Aura 481. We've talked about ways by which we keep our database or database instances highly available and scalable, but we also need to pay attention that we are able to provide load balancing features for our incoming sessions. We are actually providing customers the choice of connection load balancing and runtime load balancing. A connection load balancing is essentially based on the number of connections. So if you have 20 connections, you would get 10 on each node, assuming a 2-node cluster. With the runtime load balancing, we would actually have what we call as a runtime load balancing based on the CPU load of the system. So let's say, again, you have 20 connections, and after the third connection, there is a lot of CPU usage on the third node. Then the rest of the connections may end up on the second node because the connection number 3 is very CPU intensive connection. And this is done by the LRICH process of the database, which is able to provide real-time load information to the database. And this is in turn, notified by the Oracle notification services to the sessions and the pools. Now let's see how this works in an animation. So let's say you have a 2-node cluster, and right now there is almost no CPU usage, and you have a bunch of users connecting. The users could be connecting using JDBC, OCI, ODP, or a connection pool. As they connect, you would see that some of them ended up on node 1. Now, as that happened, you would see the CPU usage going up, as seen by the animation on the node 1. Now, as this happens, the LRICH process will notify the database, and the database, using the Oracle notification services, will notify the sessions or the pools, whatever they may be, so that any future connections end up on node 2. This way, we can make sure that this is correctly load balanced, not just based on connection load balancing, but based on runtime load balancing, or what, and this is a choice for the customer. You would see that now, because of the extra 2 connections coming on the node number 2, it also has increased CPU usage, and this is again notified to the the open sessions. Moving on, we continue with session failover application continuity. We have this feature by which if there is a failure, planned or unplanned, excuse me, the session can fail over and continue its work. What we call as replay capability. So it's not just a failure of the session; we can also continue where left off. So let's understand this a bit better. Okay. So again, in the same case, we have a two-node cluster, and we have a yellow PDB which is running on two instances, and the users are all connecting to the yellow PDB. Okay. So obviously we were load balancing. So we have two connections on node one and two, one connection on node two. And then we find out for some reason the PDB, yellow PDB is going down, as shown by the thunderbolt of that, PDB. So as that happens, we immediately try to, figure this out, ask the session to reconnect again, and continue where it left off without having any retry logic or something specifically coded. This allows for all types of applications to immediately benefit from the failover capabilities provided by application continuity, and it does not require them to make any changes to their application. So as you can see, hopefully I've been able to convince you that standardizing your deployment on Oracle RAC allows you to future-proof your application. They have provided, there is a lot of different deployment choices that have been provided. So as you can see on the left-hand side, you have this on-premises generic to Exadata to Oracle RAC in the Oracle Cloud to Exadata Cloud Service to Autonomous Database. As we move to the right of this deployment choices, then there is a lot of choices that customers have when they want to use RAC. The best part is you could move between deployments without any changes. So if you consider our premier migration tool, which is zero downtime migration, you could move from your on-premises generic into the Oracle Database Cloud Services in our Extreme Performance Edition, or you could use the Oracle Exadata Cloud Service, or you could use move it to the Autonomous Database. So as you can see, we provide you with a wide variety of deployment choices. This is why I think that I can summarize that Oracle RAC not only meets but exceeds all your requirements to seamlessly future-proof your application. Remember that I have spoken about no changes to your application at least 5 to 6 times in this session. So that is the most important key term, in the sense that Oracle RAC or standardizing on Oracle RAC will help you future-proof your applications. Now let's summarize some of the key requirements. So yes, we required scalability in HA, and yes, Oracle RAC does provide you scalability in HA. We have a broad application support. Yes, we do that. We also have a multiple deployment choices, and we have the ability to seamlessly, workload management solutions provided for you. I would definitely recommend that you look at the other sessions in the area of disaster recovery and availability, which is basically my colleagues' Oracle Active Data Guard disaster recovery tips and tricks. And obviously, you definitely do not want to miss the maximum availability architecture blueprints, because Oracle RAC and Data Guard are somewhat of the crucial components of MAA. Finally, I would definitely recommend you to check on the hands-on lab, because remember, we talked about services and application continuity and load balancing. Well, we have a hands-on lab specifically catered for showing and demonstrating those things, so you could see this in your at your own time. Finally, I would like to take a moment to thank you all for attending this. If you have any questions on this, please do reach out to me at RACMasterPM on my Twitter handle. I've also a bunch of blog posts and presentations from my previous speaking engagements that you may find in my LinkedIn site and the SlideShare site. Once again, thank you so much for attending. It was a pleasure.